So intermolecular forces can determine what phases something can be. So, and things can change phases. Evaporation is going from a liquid to a gas. And sublimation, and of course going from a liquid to a gas, there's going to be an increase in that kinetic energy. Sublimation is being able to go from a solid to a vapor or gas without becoming a liquid. So why does this happen? And it's the Boltzmann distribution curve. So we have number of molecules, and then we have molecular speed or velocity, and if we plot that we get a Boltzmann distribution curve. And let's see how good I can draw it. May look something like this. And at some point, find another marker here, there's a threshold energy, and I'll just call it E. That's a certain percent or part of the molecules can exceed that. Molecules that have a greater speed than this have enough kinetic energy to escape into the vapor phase. With enough speed or kinetic energy can escape. To the vapor phase. So in other words, we have a liquid. It can become a vapor or a gas only if the molecules have enough kinetic energy to escape, and we're eventually going to call this, let me see here. So if I have a flask has liquid in it, there's going to be some molecules that can escape into the vapor phase. And you've seen that condensation inside a bottle when you put something in the refrigerator. You've actually, by cooling it off, you've got to seal the bottle. By cooling it off, the molecules in will condense because temperature affects how fast molecules are moving. And at some point in time when it's sealed off, some of the molecules then become supersaturated. They will now become a liquid, and this I like to call dynamic equilibrium, when there's a balance. But it only happens in a sealed container. So then what happens if we increase the temperature? So this is for a given temperature, let's say 25 degrees. So what happens to this curve if we change the temperature? Actually, then the molecules get redistributed, and then let's say this is 100 degrees Celsius. We have more molecules that can escape into the vapor phase because we've added heat. Adding heat causes an increase in the kinetic energy, which allows more molecules to exceed this escape. I'll call it escape velocity. Usually in physics we talk about escape velocity in terms of escaping the gravitational field, but they gain enough energy to break that intermolecular force. Because gases, for the most part, vapors have very, very, very minimal intermolecular forces. Some books may go as far as saying there's almost zero intermolecular forces. So that is what you're breaking by adding the heat. You're weakening or breaking the intermolecular force. So if we plot pressure versus temperature, let me see if I can see this. And my diagram is not going to be exactly to scale. So the first one I'm going to plot is ether. It's supposed to be CH3O. These are the molecules I am going to compare. CH3, CH2OH. I'm going to do water, and I'm going to do ethylene glycol. So I have to look at ether, the very first one. It only has dipole-dipole. The oxygen is slightly negative, the carbons are going to be positive, but no hydrogen bonding. Its vapor phase diagram may look something like this. I'm going to put a 1 on it. And one thing I am going to put is this is 760. At 760, that's when that boils. So if I did now the same thing for ethanol, it's going to look something maybe something like this. Let me see if I got a different color here for, thought I had a different color. Oh, it disappeared. We'll go blue. It's probably not going to look as neat. So if we did water, ooh, that smears. Let's go back to pink then again. Water, it's going to look very similar because it has hydrogen bonding, and it's a smaller molecule. The hydrogen bonding can get closer, so it's actually going to boil at a much higher temperature. If we got ethylene glycol, it's a small molecule. There's 2 OHs. Let's use white. Boiling point is going to look something like this according to the books. And with this can all be explained. So we can explain the vapor pressure in terms of its intermolecular forces. So the first one only has dipole. So it's going to have a much lower boiling point. This is the boiling point right here. Ethanol has hydrogen bonding. But the molecule is pretty large. The hydrogen bonding can't get as close to each other. So this is the temperature in which it's going to boil. And I didn't continue my diagram. For water, it also has hydrogen bonding. But since it's a small molecule, the hydrogen bonding is going to be a tighter bond. So it's going to boil at a little bit higher temperature. And ethylene glycol, I'd have to continue it on out, has 2 hydrogen bonds. So it's going to boil, I don't remember if it actually is curved or straight, it's going to boil someplace up in a much higher temperature. So what I'm trying to do is vapor pressure changes as the temperature changes. So as temperature goes up, it's not a linear model. As temperature goes up, as temperature increases, the vapor pressure increases. which means, going back to that molecule, that one drawing again, the Boltzmann distribution. So at one temperature, it may look something like this. Remember that energy? And when you heat it up, it's going to get a redistribution of curve. So anything past this kinetic energy, threshold energy, is going to become a vapor. And the more vapor that you have, more molecules escaping into the vapor pressure is going to increase.